presentation, entire screen. Entire screen. Whoa, all right, here we go. So, we are going to start with problem number 1 on homework unit 13, which is like forces and torques on currents. Okay, so our first problem is a magnetic field going into the board and we have a current loop. It's an equilateral triangle. Current going this way. And let's see, what else? Okay, so what does it give us? It gives us the side length is 8 centimeters. The current is 1/4 amp. And B field is 1.3 Tesla. That's it. So now, basically, it's spun around. So that it is going the opposite direction. So now the current is going this way. Okay. Awesome. So the equations we're going to want to use are basically we're looking at the energy in this system. So the equations we're going to use, I'll box them in over here. We're going to have that U equals negative mu dot E. So that's the potential energy. And we also know that delta U is negative work. And mu equals NIA. So that should be the 3 equations that we're using. That should be it. So going through these, to find the potential energy, we need to find mu first. So let's do that to begin with. We know that, so I'll work down here. So mu equals N, which in this case is just 1 turn. The current is given over on the left there, 0.25. And the area of an equilateral triangle, you can look up the formula for that. It should be, well, it's 1/2 base times height for a triangle, right? And so we know the base is just 0.08 meters. The height is going to be, so this is 1/2 times the base, which is given, and then the height is going to be 0.08 times the cosine of 30 degrees. And that's because if you look at an equilateral triangle, every angle here is 60 degrees, so we know that this one is 30. And if this is 0.08, then this length right down here should be 0.08 cosine 30. But that's geometry. You guys can do that on your own. But so that's pretty much, this should be your mu right here. So once you plug that, all those numbers in, then you simply you find your initial is going to be negative mu dot B. And these are actually vectors. But the sign is always going to be horrible for these. There's a ton of negatives. Yeah, I mean, and the homework should tell you that it's negative, but if it doesn't, then we'll try and get the right side on the first time. So if your U is negative mu cross B, so you plug in your U, and we can actually calculate that real quick. I didn't bring it down. What's up? Yay. So if all the numbers are correct, then I'm gonna go back. Delete. I just want to get rid of the cosine. Or you just got rid of it. Get a cosine. So we get 1.234 times 10 to the negative fourth. 1.20. That's our mu, negative mu, dot, and then the B field is in the negative, negative direction. And actually, if you look at our picture, you guys can't see my hand, but if you take your hand and put it on the screen, or Alyssa can watch, when your fingers curl with the current of the left triangle, your thumb will be pointing out of the screen, and the arrows are pointing into the screen, right? And so that means, since it's negative mu cross B, given by this formula right up here, you're actually going to get a positive number because you're going to have negative the 1.3 Tesla because they're going into the page. And so you're actually going to get a positive U initial. So if we multiply that by 1.3, and then we should get our number.
1.60 times 10 to the negative fourth.
So that's our initial energy, and then our final energy is just going to be the opposite of that, because then our mu this actually will have a negative sign of its own, since in the right triangle, if you follow the current with that one, it's pointing into the board, so it'll be like a triple negative basically, but you'll end up with the negative answer from that first equation. And then you just do delta U equals work equals U final minus U initial. And that should give you your answer. Does that make sense?
Yeah.
So
yeah.
U initial, we use negative mu dot B. And it's negative mu, so you have negative, and then this is mu, and then we have B, which is in the negative direction. That's how it was given, right? It's going into the board. And then U final just has to be the opposite of U initial, because now both arrows are pointing in the same direction. The problem with potential energy with current loops in B fields is that they're just defined really weird. Instead of being defined like at 0 when they're facing the same direction or something, they're defined at negative. It's very weird, but so this should be your answer right here. And then delta U equals W. That's just changing in potential energy is work. That's a basic. That's like physics 1 too. You use that as well. So you should know that formula. And so then yeah, it should just be U final minus U initial, which will just be actually twice this. If that makes sense, because it's the same magnitude pointing in opposite directions. So that should be problem 1. Okay, does that make sense? Not problem 1. It's wrong.
You final. I took this, subtracted it with this,
And it was wrong.
Mm-hmm.
You can see if I got the numbers right.
It's because I know my numbers are exactly the same.
Hold on. Oh, you know what? I think it's the area of the triangle.
Yeah.
Because that didn't work out earlier. Hold on. Instead of using the area of the triangle that I used, well, actually just look it up. Area of an equilateral triangle. And then plug in 0.08. Okay, square root of 3 over 4. So use that and see if that gives you the right answer. So, yeah. (2.77 times 10 to the negative 30). So instead of using the 0.08 times the 0.08 cosine 30, use this and see if that gives you the right answer.
That just
You should just replace it there.
be negative or positive?
It'll be negative.
Yep.
Okay, so why did that not work? Okay, well, I'll figure that out later. Anyway, so use this for the area of the equilateral triangle. Just look up the formula for that.
Root 3/4 side squared.
Root 3 over 4
Side squared.
a squared is area of an equilateral triangle. Area. Okay, I'll go over my geometry then, geez. Okay, but the other formulas were right, it was just the equilateral triangle formula. Okay, next problem is the current loop in B field. So we have, let's draw our axes first. Okay, move to our B field loop. Okay, B field, then we have our wire loop, and it actually gives us the angle. It's at a 30-degree angle. You can see that in that second paragraph. This is 30 degrees, and this length is 0.1 meters. Let's see, other information given. B field is what, 1.8 Tesla? And actually you could put I hat here if you want to, because this is important. B is always a vector, so it is important to know which direction it is in. So yeah, D is 0.2, so that would be this length, is 0.2. We'll get to there. The current in each, well, A is, okay, it's 0.85 per turn. 0.85 amps per turn. What else is given? Oh, and N equals 12. Okay, so there's two ways to do this problem. Either you can use the torque equals mu cross B formula, but I'm not going to use that one. I'm going to use the force formula. So I'm just going to use F equals IL cross B, because I find it easier to use. You don't have to get as caught up in the cross products and stuff. They turn out to be easier because they're always just perpendicular instead of at weird angles. So basically, we're going to be looking at how the torque is going to be, how much torque is going to be on this square, and then which side we need to hang a weight from. So basically, we're going to hang a weight either here or over here to counteract that the fact that the square wants to spin in this magnetic field. Does that make sense? Yes. Okay. So the first thing we can look at is the two sides that are facing us. So this front side. Okay. We're gonna. If you look at the picture, it's actually not labeled, but anyway, it's the bottom side. And the reason it's not labeled is because it's actually going to be counteracted by the other side, so there's going to be no force on it. You have a current running up along this way, and so if you have the current running this way and the B field going down, that's going to be, the force is going to be into the page, and on the other side it's going to be out of the page, and so those are just equal and opposite forces. There's going to be no torque due to those forces either. So they aren't really affecting it at all. What will affect it is side C and D. And so we're going to look at side D first. So if you look at the second picture, we can see that the current is coming this way, and then here's side D and here's side C. So the current is running like this. That's like a top view of our loop. And so inside D, it's running into the page. So if it's running into the page, you can put your thumb into the page and your fingers along the direction of the B field, and your palm will be facing down. And so the resultant force here is going to be this way. And on the other side, on side C, you're going to have the current coming out of the page. So if you put your thumb in that direction and your fingers along the B field, force will be going up. And that's why there's a torque on the square. Does that make sense? So this square basically gets flipped onto its side, right? And then over here. And so then you have D, the current comes up and then into the board and then down and then out of the board. And so since it's going in here, curl your fingers that way, down, and then out, curl your fingers to the right. So now we need to find what kind of force is that? What's the magnitude? So we're going to use the FIL cross B formula up here. So the force is going to equal the current, which is 0.85, but that's amps per turn. And so we need this in amps, so we need to multiply this by 12 turns, right? So that these two will cancel. And then we need the length, which is going to be 0.2 meters because it's a square, so all the sides are the same length, 0.2 meters. And so that's good. And then we cross that times B, which is just 1.8 Tesla. And this is the reason I'm using the force equation is because you don't have to worry about the signs here because they're at right angles. Because the current is running straight into the board and the B field is aligned with the x-axis, basically you can just get rid of this cross product and just multiply it. Because you're multiplying it by the sine of 90 degrees, which is 1. And so then you don't have to worry about it. So that's the force, one of the forces. So what is that number?
0.03672.
Okay, and that would be in newtons.
0.2 or 0.02 meters?
Ooh, good call. No, it is, each side is 20 centimeters. So it is 0.2. 0.2
It might
meters.
be off one decimal place.
Oh,
I'll
okay.
just move it up one.
So you multiplied it by 0.02, so it should be greater, right? You should put 0.362, 3672.
Yeah.
Okay. All right, so that's our force. Now, we need to find the torque though, and torque is given by torque equals F cross R, or R cross F. It's R cross F. Whoa. So, what is the radius in this case? Well, the radius to the force, and this is physics 1 again, so the radius is how far perpendicularly is the force from the center of rotation. So the center of rotation is at 0, 0, right? We know that. It's at the center of our graph. The radius is not the 0.1 meters. It's not this length. The radius is actually going to be the length from 0 here perpendicular to that, to the force. And so what we're going to have to multiply this by is actually, so you, 0.1 times the cosine of the angle, 30 degrees. So that's going to be your radius for the torque. And then you're going to multiply that by the force, which we have 0.3672 newtons. So that's our torque due to one of the forces. So what did you get for that? Did you plug it in? That's degrees. You can use pi over 6 if you want to use radians.
Point 318.
Okay, and that would be Newton meters. Whoa. Okay, so that's the torque due to one of the forces. We're just going to multiply that by 2 to get the torque due to this other force, because they are causing the same direction of torque. So this is actually 0.318 in the negative k hat direction. And that the way you figure that out is basically which way is the loop going to spin? Well, it's going to spin so that this point is going clockwise, right? And if you follow that curve with your hand, then your thumb is going to be pointing into the screen, which is in the negative k hat direction. And the other force will cause the same direction spin. So both of those are acting along in the same direction. Both are acting in the negative k hat direction. So you're just going to multiply that by 2 to get the total torque. So that should just be 0.0636 Newton meters in the negative k hat direction. Okay, so I'm going to erase this top part here, because now we need to figure out which side we're hanging the weight from. And we can actually find that out right now. We know that if this is our loop, it wants to spin clockwise. So we're going to have to hang a weight over here to counteract that motion. And it says in the problem that if we're hanging it on the C side, which is over here, it's going to be a positive number. So our weight is definitely going to be positive M. We already know that. But now to find the magnitude, well, we have our torque, and we needed torque to counteract that due to that mass. So your torque is 0.0636 in the negative k hat direction. So we can put that here, negative k hat. And then this has to basically, so plus your mass times gravity times the radius, right? So this is your force, and this is your radius, right? That's like this formula down here, torque equals Fr. That will have to equal 0 because we want 0 torque on this square. And so gravity we know is 9.8 meters per second squared. And the radius is actually going to be the same as the radius on the other one because we're hanging it at the very end. So we're hanging over here, and this radius is going to be the same as the radius that we did earlier right here. It's going to be right here. So it's going to be the same 0.1 times the cosine of 30 degrees. And so then you basically just solve for m, and that should be the end of the problem done. Okay, let me check your numbers. Let's see. I just did it all. You didn't put a cosine 30 in there. So that's one thing.
Still super slow.
I think you're off by a factor of 10. Make it nice bigger. Oh, yeah. That's it. So I'm not sure then where you make something up. I mean, it must be here, right? So our torque is still too small. So I think here. What do we do? 0.2, 0.8512. That should all be right then. Yeah, I don't know. Anyway, but so it should give you point what? Yeah, 0.749 roughly is the mass, 0.749. Yeah, just check your units. In here, check this number, 0.3672. It might be off by a factor of 10. So check my units on this equation, and then plug it into here and just make sure that you're using 0.1 cosine 30. That should be all right. And then you get this number, which is probably off by a factor of 10 now. Although, yeah, anyway, multiply by 2, and then make sure that over here again, you're dividing by 0.1. Actually, I mean, so you have 0.1 cosine 30, but basically, to find m, so to solve for m, you're going to have m equals, so the negative turns positive when you flip it over, so you have 0.0636 over 9.8 times 0.1 cosine 30 degrees. And actually, if you go through all of this and leave it all in variables, you can cancel out this r, which is really cool. But we aren't going to do that right now. But yeah, your mass is right around 0.75 kilograms. I'm not going to go through the whole problem, but I'm going to show you guys what you can also do. We know that the current is flowing this way, because that's given. And so what you can also do, instead of looking this as forces on wires, you could look at it as the mu vector trying to align itself with the B field, right? And so the mu vector for this loop is this way. This is your mu vector, and this mu vector wants to be pointed in that direction, in the positive x direction. And so you could also use the torque equals mu cross B, I think, or is it dot B? Yeah, mu cross B. And so you can go through this formula. It might be more confusing because when you're doing your cross product, your mu vector is not pointed in either the x or the y direction. It's pointed in a little bit of both. So you're going to have mu, the magnitude of mu, times like the cosine of 60 in the I hat direction, and mu plus, or, oh, this is actually negative, and then mu sine of 60 in the j hat direction. And so you just need to be careful, and then you're doing the cross product. So just be aware of that. If you guys want to try it, it's great practice, but it might be more confusing on this one. I think that's it for problem 2. So. All right, I think I'm going to finish recording because time is almost up. But yeah, just come to the sessions and you can ask questions to me in person.